All right, let's talk about section 12.4. So in 12.4, we're going to be talking about light and how we can see it in specific forms like holograms, how it's going to be polarized, and how we can use optical fibers to transmit lasers and stuff like that. The first thing that we're going to talk about is polarized light. What exactly is polarized light? So if you look at the definition of polarized light, ignore my beautiful diagram of me for a second. But polarized light is basically the way that a wave is going to move or oscillate, and it's going to happen in more than one direction or orientation. So for example, when we talk about a transverse wave in the regards to rope, okay? So if we look at this diagram over here, okay, so if you see Mrs. Fry right here and she's holding a rope and she's moving the rope up and down, it's moving in a transverse wave. A transverse wave is basically the motion of, so for example, if I move this rope in the transverse wave, I'm moving it in a either horizontal motion or a vertical motion or somewhere in between. That is how this rope is going to move. So when we talk about transverse wave, we can say that it's also going to move in a horizontal or vertical or somewhere in between kind of motion. So that is how a polarized light is going to travel. A polarized light is going to travel in a transverse wave, meaning that it can move in more than one direction, and it's going to have the property of what a wave looks like. So I use the example of a rope because it's easier to visualize how a rope moves. You can think of a light moving in that same way. Now let's move on to what exactly happens when we have a light wave. So when you have a light wave and it's vibrating and it's moving, right, it's going to move in the same direction as its electric field or its magnetic field. All right, so light wave is going to move or vibrate in the same direction or with the same kind of vibration as the electric field or the magnetic field of the light's wave. Now, one thing that I want you to know is we talked about this in a couple chapters when we talked about magnetism and electromagnetism and stuff like that. The electric field cannot go in the same direction as the magnetic field. It actually moves perpendicular. So the electric field is going to move perpendicular to its magnetic field. That's why I have or. If I didn't have that or, it would not make sense. So even though a light's wave is going to mimic the same direction or vibration as its electric or magnetic field, it cannot follow the pattern of both of them because electric and magnetic fields are going to be perpendicular, not parallel to each other. So because we talked about a light's wave is going to move in a transverse wave, that means it's going to move either horizontally or vertically. There's another name for a wave that actually only moves in one direction. So for waves that only move in one direction rather than horizontally and vertically or in between, it's going to be called linear polarized light. So light that moves in this kind of formation means that it's going to move or vibrate in only one direction. All right? So the light and its magnetic field is going to only move in one direction versus many directions or kind of switch back and forth. All right, so let's talk about polarizing filters. We talked about what polarizing light is, and basically it's when light can move in more than one direction like a transverse wave. So how exactly can we build a polarizing filter? So we know that a light can be polarized, but how does that happen? The way that happens is we create a filter, and that filter has lines of crystals that look like parallel slits. The best way to portray this is through a diagram with a fence and a piece of rope. If you go to page 384 in your textbook, you can kind of see it, but I drew it out for you guys to kind of better understand it. So if I have a fence, like over here, and I have a piece of rope. So let's imagine that this rope is acting as a light wave, and this fence is acting as crystal slits. So what's happening is this fence is located, it's standing upright, so it's parallel. So when this light wave comes in and it's going in the same direction, or it's moving with the same vibration as the crystal slits are located, it's going to be able to move through those slits with no issue at all. All right, so the fence is standing upright. The wave that the light or the rope is having is also going up and down. So it's going in a parallel motion with the way that the fence is located. So I have right here, only light waves with magnetic fields that move in the same direction as lines of the crystals can go through. So the fence is upright and the rope is moving up and down, so it's moving with the same parallel motion that the fence is located. So the rope is easily able to go through the fence. But if I look over here and I flip the fence on its side, it's no longer parallel. The rope can no longer go through the fence in a correct way, and so when the rope comes out, it's going to look a lot different and not be in the same wave format as it was when it was entering the fence. So that means that the wave motion is blocked in this fence, but it's not blocked in this fence. This is a good way that the polarized light can go through, and here it cannot. So if I look in their book, right, and I look at this image right here with the sunglasses, it's basically saying that you have lines of light that's traveling through the glasses, and the way that the crystal filters are located in the glasses allows the light to come through. If I take another pair of glasses and overlay it on top of my original glasses, I still have some light coming through. Yeah, it's a little bit darker, but there's still some little bit of light that is coming through. But if I take one pair of glasses and I flip another pair sideways and put it on top, there is no light coming through because the light wave cannot get through those slits that the crystals make, and therefore I cannot see anything, and so the light cannot be polarized. If you guys are a little bit confused on this, just watch this video, or just go in your textbook and read this little paragraph and then look at these two diagrams. It explains it really well. Like I said, if you have a fence that's standing upright, the motion of the rope, which symbolizes the light, moving through the filter symbolized by this fence, they're both moving in the same way, okay? The rope is moving parallel to the way that the fence is standing up. Here, the fence is on its side, not in the same way that this wave of rope is moving. Therefore, it cannot come out still in its wave format. It comes out disassembled, and therefore you do not have proper transmission of light. Let's talk about polarized lenses. So when I look out on a lake and it's beautiful, I can't stare out for much long without squinting or covering my eyes because of how much the glare is on the water. So the way that the light from the sun is hitting the water, it produces this glare that's pretty painful for our eyes to withstand just on their own. So we usually pop out our cool sunglasses, put them on, and it feels a whole ton better. But why? And I'm about to tell you how that kind of works. So if you pop on your sunglasses and you look out into the water, you feel like your eyes have just gotten a ton of relief because that glare doesn't really bother you anymore, especially if you're wearing polarized sunglasses. So this is how polarized lenses work. So polarized lenses usually have some kind of chemical that's painted onto them that helps prevent the glare from getting into your eyes. But what's interesting is the way that the chemical is actually painted onto your glasses. If I look out onto the lake without any sunglasses, the way that the light is reflected off the lake comes back in a horizontal reflection. So to counteract that, they paint the chemicals onto the polarized glasses in a vertical motion so that the glare kind of gets canceled out by the vertical motion painted onto our sunglasses, and the glare is no longer existent as it enters our eyes. So it's very pleasant to watch the lake or the ocean and not feel pain because of how bright the sun is. Now, if you looked at the diagram that I just spoke about on your on page 384, this is the way it's working. So I have polarized, if I have sunglasses, right, and I have them on top of each other, they're overlaying each other, they're still going in the same motion, so I'm still getting some kind of light. But if I have a a wavelength that is coming in one direction and I flip another pair of sunglasses going the opposite direction, they cancel out and there's nothing coming in. So that's kind of the same idea when I talk about the way that the glasses work. I have polarized lenses that are canceling out the glare by the way that they're painted on, so that the horizontal glare that's coming off of the lake is no longer affecting our eyes because of the vertical way that the chemicals are painted onto the glasses. This helps us to look at beautiful views without being affected by their nasty glares that can really damage our eyes and really make us uncomfortable. Alright, let's talk about holography. Have you ever been to a museum and you walked through this section where they have 3D images and they kind of look like they're floating around? And as you walk at different angles, you can tell that at different angles it kind of looks like the object is shifting position, or if it's like a human person, like a picture of a human being, it kind of looks like their eyes are following you. That is called, they're pretty much holograms. And the way that holograms are made is through the technique called holography, which is pretty much them making a 3D photo of an object. So that object isn't what you're seeing isn't actually the object, it's being reflected in a way so that it creates a 3D image. Sometimes you can see these on credit cards. It's like, it looks like a little bird is flying, and that's a type of hologram. So how exactly are holograms made? Let's go into that. Alright, so how exactly does a hologram work? I kind of drew a brief picture. I got this idea from a YouTube video about how 3D holograms work by someone named Physics Girl. I'm going to attach that video to the grade link under my teacher's page for this assignment. So please be sure to watch that because it's very, very informative and it kind of puts everything together. So I'm going to show you how this works in a more visual form so that it makes more sense than if I just wrote it in words. So basically, if I have a laser, right, and it's coming out of this laser instrument, right, it's going to go through something called a beam splitter. Basically what's going to happen is that laser is going to go through and it's going to be split. And it's going to go in two directions. One is going to go through a lens. It's going to hit the mirror, and then it's going to bounce off the mirror, be reflected off the mirror, and it's going to hit the object. Once it hits the object, it's going to be reflected onto the holographic film. Alright? This type of beam that's doing this, going through the lens, then to the mirror, being bouncing off the object, and to the holographic film, this is going to be called the object beam. Alright? So I'm going to label this the object beam. So, I'm going to repeat that. The laser is going to come out, it's going to hit this beam splitter. One part of the beam is going to go through the lens, hit the mirror, bounce off, be reflected off the mirror, bounce off the object, and it's going to hit the holographic film. Alright, that's called the object beam. Now another wave of laser is going to come, be reflected off of this mirror, go through this lens, and it's not going to hit the object. In fact, it's going to go directly to the holographic film. Alright? So this laser beam that has gone straight to the mirror, reflected off the mirror, through the lens, and onto the holographic film, this is called the reference beam. Alright, so I'm going to write it over here. Now, once they both hit the holographic film, initially the light that is from both of these beams, they're going to create a funky pattern. They're going to kind of create this pattern that kind of looks like a checkered mess if you actually look at it very closely. Alright? So if you look at it very closely, it's going to look like this checkered mess. And they call this the interference pattern. Alright? So this interference pattern is going to be made from the light that is coming from these two beams. But it's actually going to create an image because of the laser that is going to come through and hit it to make the image actually appear. Alright, so I'm going to repeat that one more time. So you have a laser that's going to come out, It's going to be split in two because of this beam splitter. One part of the laser is going to go through the lens, be reflected off the mirror, hit an object, and that is going to be hitting the holographic film. That's called the object beam because that beam is hitting the object. The reference beam is going to come out of the beam splitter, hit a mirror, be reflected off that mirror through the lens, and hit the holographic film. When both of these beams hit the holographic film, it's going to kind of make this funky pattern called the interference pattern. That interference pattern kind of looks like a jumbled mess because it's the light that's being created from the two beams on the film. But it's not going to look like the image. This does not look like the tree. But when the lasers come and hit it, it's going to make the image look like the image. It's going to make the image look like the tree, and that's what creates the holographic image. Alright, so let's kind of compare the difference between a regular picture and a hologram. So a regular picture is kind of like a 2D picture that you can take on your phone, print out, hang on your walls, and then a hologram is that 3D image that we talked about with the lasers and stuff. So when you have a regular picture can capture brightness or the intensity of light that's being reflected by an object's surface, but that's about it. It's easy to copy. It's going to give you details, but not as much as a hologram because it's not 3D. It's only two-dimensional, so you can only see so much. A hologram, on the other hand, it's going to capture two things. It's going to capture the direction of the light and how intense that light is. It's going to give you a lot more details to the eye because of the direction and the light, making it 3D. It's going to be way harder to copy. You can't just easily copy it because of the three-dimensional shape to it and because of how many different directions the light is traveling. But there are a lot of important uses for holograms. So I said that sometimes credit cards have it, driver's license have it. They help to prevent counterfeiting because you can't recreate it as easily, therefore hard to copy. X-ray lasers use it. A lot of scientists, they actually are able to use holograms to display really, really small microscopic cells and organelles of the body and in cells. So that's really important uses that holograms have versus a regular picture that, say, you can take on your phone or a camera. Alright guys, on to the last bit on 12.4. So we just talked about holograms, but now let's talk about optical fibers. Optical fibers are basically used when you need to get to hard to reach places or super long distances that you can't have lasers reach them. So they help to transmit light to these far fetched areas and stuff like that in an easier way rather than you really having to stretch yourself out. So the way that they transmit this light to these far distances is through something called total internal reflection. In the next couple minutes, we're going to get into what total internal reflection is, but before we get to that, I need to tell you guys about other types of reflection, so it kind of makes sense when we get to total internal reflection. So one type of reflection is called partial reflection. Basically, this is when some of the light that you have is going to be refracted into the air, and that's only going to be a little bit. More of the light is actually going to be refracted back into the water if the light source is underwater. So I'm going to go over a diagram that's in your textbook. That's on page 386 if you want to follow along. It's figure 22. But before we get into the diagram, I want to go over two other kinds of reflections. Alright, so another type of reflection, if you have a source that's underwater, is going to create something called a critical angle. And the way that a critical angle is created is if that you have that underwater light source and it's aiming at an angle at the boundary of the water. So boundary of the water means pretty much where the top of the water meets the air. So when you have this angle of light coming at this boundary of water, you have a ray that's being refracted. But the ray is being refracted and is being bent at such a specific angle that that ray of refraction is actually not even going to come into the air, but it's going to follow the path of that boundary. So it's going to follow the waves of that water. You're not going to see that light go out into the air, but you're going to actually see it follow the waves of the water, the top of the water, and some of it will be refracted back into the water as well. So that's critical angle. Now, the last thing is called total internal reflection. What total internal reflection is when you have a complete reflection of light at the boundary between two different materials, such as air and water. So that means your light source that is shining up at the water is in such an angle that there's a boundary between two materials, such as the air above the water and the water that you're in, that it's going to create a complete reflection of light, almost as if there was a mirror that was on the boundary of that water. Okay, so as if there's a mirror, pretend there's a mirror on top of the water level, and you have a light source that's hitting it, it's going to be reflected right back into the water because of the reflection. Now, when this happens, the angle of the light is actually going to be a lot bigger than the critical angle. The critical angle causes water not to be refracted into the air, but it's going to follow the boundary. But this one is going to go right back down into the water and not follow the boundary of the water at all. So for total internal reflection to happen, you're going to have light that is going to travel from the source a lot slower in the first medium, which is water, than the second medium, which is air, and it's going to hit that boundary between the water and the air, and it's going to create such a greater angle than the critical angle that it's going to act as if there's a mirror and be completely reflected back into the water. Alright, so now let's look at a picture that you have in your book. On page 386, figure 22, we see that we have three light sources. So we have these three flashlights. So the first figure that we see right here, it shows that the light is being it's shining at an angle, but you see the normal light, right? But the normal kind of comparison in the middle in the red. And you see that as the light is being shined at an angle, some of the light is being refracted into the air and some of it is coming back into the water. So this is when we talked about partial reflection. So you have part of it going into the air and the rest of it is going back into the water. Now, when you have more of an angle and you're shining the light at the boundary of the water, you're going to create a critical angle. So this angle is very specific, that the way it is shining is actually causing the light to travel at the boundary of the water and is creating a critical angle, and the rest of the light is being refracted back into the water. And then lastly, you have total internal reflection. So this angle that this light is shining is at a specific angle as well, greater than the critical angle, but it's acting as if there's a mirror right here, and it's not even going across it's not even going with the boundary like it is here, or it's not being refracted into the air like it is here in partial reflection, but it's actually acting like there's a mirror and it's going right back into the water. So that is when you say that you have total internal reflection. Now, for total internal reflection, we can relate that to optical fiber. So inside of an optical fiberglass, I'm going to show you a picture over here. It's on the next page. It is on page 387, right here. This is an optical fiber. So you can see that on the outside you have plastic for protection, and then on the inside you actually have a glass layer and something called a glass core. And what's cool about this optical fiber is that it's made out of two types of glasses, so that means there's two types of index of refractions that are happening, which is actually a really good thing. Because of the two types of index of refraction that's happening, when you have light that's coming into this optical fiber, the light kind of looks like water because it's just able to flow right through the optical fiber, travel fast, and able to get to the destination without any hindrances because the light is bouncing off of the glass core and it's able to move very quickly down the inside. That is why optical fibers are really great uses for long distances when you need to convey a message or have some kind of movement. So if you actually look on YouTube and some articles, you can actually see that optic fibers are used underwater in the oceans for internet and for some types of communications, because they can go long distances and they travel very, very fast. So The cool thing that is that when the light is traveling through and it's bouncing off and it's traveling down, they're actually not being absorbed by the sides. They're being very well conserved inside so that they are not being wasted in any way. But all of the light that goes in will come out on the other side of the optic fiber. So what are some uses for optic fibers? So let's look at that. So some uses for optic fibers are, one, you can use them for telephones. Like I said, telephone lines can use optic fibers to transmit over long distances. TVs use optic fibers, computers, like I said with the internet. Medical uses, they can use it for heart catheters to put them in. They can be used to reflect, look into a human body to see if there's any diseases or disorders. They can create, they can help with blockages of the heart. So they're very, very important in medical uses. There's also another way that you've seen practical, in a practical way you've seen optic fibers, and there's something called optical scanners. They're different from optical fibers, but they kind of work in a similar way in that optical scanners are pretty much a device that is going to read the intensities of reflected light and then convert that information that they get into a digital signal. So for example, when you go to the grocery store and you either are self-checkout or someone is scanning your groceries, they are actually using optical scanners. And the way that it works is that you have the scanner, it's going to scan the barcodes, which are those like thin and thick lines that make up the barcode. And as the scanner scans this barcode, it's going to create an electrical signal. That electrical signal is going to be going into that computer database, and it's going to look up for the price for that item that was just scanned. Once it finds a price, it will send that price to the cash register, and it will come up and say your broccoli was $1.49 or your cheese puffs were $1.99. Why cheese puffs are more expensive than broccoli? I don't really know. But, so that's how optical scanners work.